Section 3-7 is on the derivative of composite functions. And the objective of this section is, given the equation for a composite function, write the equation for its derivative function. If you recall, in the section 3-4, you've learned some techniques for finding derivative functions. You've learned some rules already. We have what we call the power rule, which is the rule for taking the derivative of a power function, thus the name. We have the rule for the derivative of a sum of functions. We have the rule for the derivative of a constant times a function, and we have the rule for the derivative of the constant function. You've already seen those four. And actually what we're going to see over the remainder of this chapter and next chapter is that there are a bunch of other rules that we need to learn in order to find the derivatives of all types of functions that we want to be able to work with. And so we're just going to keep adding to that list of rules that we know for taking derivatives. So the one we're going to learn here today is the rule for the derivative of a composite function. All right, let's take a step back here actually. We technically kind of skipped over section 3.6, and it's not that the information there was not needed. We actually do need to talk about one topic here, and that is the derivative of sine and cosine. So here are two more rules that you're going to learn prior to getting your rule for the derivative of a composite function. But the way we're going to look at this for right now is just to look at an example, or I should say to explore the derivative graphically is really what we want to do. And we'll do this with just an example here, I guess is how we'll write this. But it says to graph the function y equals, or f of x equals sine of x. And it says also to graph f prime of x. Now the way that we're going to do that is using that numerical derivative technique that we've talked about, that you can use the nderiv command on your calculator to not only find the derivative at different points on a function, but I can also use it to sketch the numerical derivative of a function. So that's what we're going to do. So let's switch over to our calculator. And let's go to our y equals menu. We'll put in sine of x. And we will put in the numerical derivative of y1. My variable is x, and my value is x. So there's how we sketch the derivative of sine of x. And for my window, I'm going to change this over to, since I know the range of my sine function goes from -1 to 1, I'm going to go from -5 to 5. It'll give me at least a little better picture of this. You could go zoom in further if you wanted to, but this should be fine for what we're doing. Now, let's take a look at what the graph of this looks like. Graph. Here's our sine function being sketched. Notice it crosses the through the origin there, increasing as it goes through the origin. And here comes in our sketch of the derivative function. That actually looks very familiar. It looks very similar, if not identical, to that sine function we just sketched, except for it's crossing the y-axis there at 1, y equals 1, rather than going through the origin like we saw with the sine function. And actually, that looks a lot like the cosine function. The cosine function has the same shape as sine, and it crosses the y-axis there at 1. In fact, let's check to see if that is the case here. Let's go to y3 and have it graph the cosine of x. And we'll graph this with that little circle there to trace it so we can see if, in fact, it sketches right on top of that numerical derivative. And there you go. What do you know? It's actually sketching right on top of that derivative function. So it looks like the derivative of sine is cosine. In fact, that's our first property from section 3.6 that we need to note here, is that the derivative of sine of x, this is one way to write derivatives. You've seen other ways that from section 3.4 that we wrote down some of our rules for derivatives. This is another way that you can do it, where we say d dx of sine of x. Remember that d dx means the derivative of, or find the derivative of, sine of x. Here we're saying the derivative of sine of x is equal to cosine of x. Now if you stop and think about this for just a second here, the fact that I started out with a function that was periodic, the sine function, which means that it repeats at regular intervals. That regular interval, the length of that regular interval, is what we call the period of that function. But the graph repeats. It goes through the exact same y values over and over and over again. It oscillates back and forth, which means the graph has the same shape over and over and over again, which means it has the same slope over and over and over again. That the slope repeats at regular intervals. In other words, the derivative must repeat at regular intervals. So if we start out with a function that's periodic, we should not be surprised that its derivative must also be periodic. And that's what we have here. The derivative of our periodic sine function turns out to be the periodic cosine function. All right, so that's how we find the derivative of sine. The next question is, what's the derivative of cosine? Now, you might have an idea in your mind as to what its derivative might be. However, we'll find that there's a little bit of a catch here. So let's change this up here. Let's change this from sine to cosine. And I'm just going to shut off function y3 there for the moment, since I want to sketch, first of all, the original function, cosine, along with its derivative, and then we'll take a look at what its derivative function is. So there's our cosine function. Crosses the y-axis at 1 like we'd expect. And again, notice that the derivative function is a periodic function. In fact, it looks very similar to a periodic function we've seen before. However, this one, when it crosses the origin, when it goes through the origin there, it's decreasing. Now, sine of x crosses through the origin, but it's increasing as it does that. This one is decreasing as it does that. So in other words, it's not exactly sine of x. But if I were to take this, if I were to take sine and do a vertical reflection of it, so that it would be decreasing through the origin, it looks like that's the function that's sketched here. Well, the way that I do a vertical reflection is just by taking the opposite of my function. So let's see if that is in fact the case here. If we were to take the opposite of sine of x, what do we end up with? Look at there. That in fact is the derivative of cosine. So that's the little catch that I mentioned there, that you know, before you started this one, you might have guessed that the derivative of cosine was going to be just sine. You're close if you thought that. Turns out the derivative of cosine, though, is the opposite of sine. Again, we write that as d dx of cosine is equal to negative sine of x. Again, this is one way to write out a derivative. You could also say if f of x equals cosine of x, then f prime of x equals the opposite of sine of x. That's another way you could write it out. So there we go. We got 2 more rules. We started out with 4. Now we're up to 6 here. We're adding to the power rule, sum, constant times a function, the constant function. Now we've got sine and cosine. All right. Let's continue on here and get to, I guess, really the topic of this section, which is dealing with composite functions. So a composition or a composite function looks something like this, where you have f of g of x is how we read that off. And the terminology that we use is pretty straightforward, actually, to describe the parts of this composite function. You have what we call the inside function, called that because, of course, it's the function that's on the inside here. And you have what's called your outside function, which would be function f. Function g is the inside, function f is the outside. And again, what this means is that you're going to take this value of x and you're going to plug it into function g, and you're going to get some result. And whatever result you get, you're going to then take that result, g of x, and you're going to plug that into function f. That's what the composition actually means. So not only are you just taking x, or not only are you taking x and plugging it into one function, in this case g, you're then taking that result, the output, g of x, and plugging that into function f and getting some new output. Okay? So there's a composite function. Now obviously this is just showing 2 functions really that make up that composition. You can have as many functions as you want that make up your composition, thus making the function obviously a little bit more complex as you add compositions. But you're not restricted to having only 2 functions, as we'll see with some of our examples. All right, so let's take a look at an example to kind of illustrate how we could go about finding the derivative of a composite function. Now we'll in a second here put up the rule for the derivative of a composite function. But I want to take one approach first to show you one way that you can think about taking this derivative, and it also kind of helps explain why the rule is the way that it is in a second. We'll see. All right, so we have let y equal sine of x squared. Notice you've got a composite function there. You've got x squared is your inside function, and you've got sine, which is your outside function. And it says find y prime, or that's dy dx. Okay? All right, so to start off with this, we're going to just change this problem just a little bit, or rewrite it, I should say, really. Obviously, I can't change it, otherwise I would have a different problem. But I'm going to just rewrite it. I'm going to say that we're going to let u equal x squared. So we're going to let u equal the inside function. And then, of course, when I do that, I could rewrite what y is equal to. Since u is equal to x squared, that means y is equal to the sine. But rather than the sine of x squared, since that's equal to u, I can write that as sine of u. All right. Now, once I have these two here, I could find the derivatives of those two functions. So if u is equal to x squared, then I would have that the derivative of u, which you could write as u prime, but it's not very specific. Since I have different variables working in here, I want to be more specific than that. I'm talking about the derivative of u with respect to x, and so we write that as du dx. U prime, or du dx, better way to write that. Just follow your power rule here. That's all we have is a power function. Derivative of x squared, of course, is 2 times x to the first, or that would be just 2x. And I could do the same thing with y. I could find y prime, or again, based on how I've rewritten it, this is really the derivative of y with respect to u, my independent variable. See how we write that? U, derivative of u is written as du over dx. U is the dependent variable. The x is the independent variable. In the case of finding the derivative of y, here we write it as dy over du. Again, u is the independent variable, y being the dependent variable. That's how we rewrite that. So this would equal derivative of sine, we just said. Derivative of sine was cosine. Be the cosine of u. Now, I found out what du dx is, and I found out what dy du is equal to, but the whole question was to find dy dx. So I did some work here, but I still haven't answered the question. What is dy dx equal to? Well, let's explore this a little bit more closely, what exactly dy dx is. If I were to look at dy dx, dy dx could be written this way. If I look at what I have here in terms of the derivatives I've found so far, I have du dx and I have dy du. It doesn't really matter which way I write it down, but I'm going to write it down this way. If I take dy du, the second derivative I found, and if I were to multiply it by du dx, notice what happens in essence to the differentials here. Now there's technically a little bit more explanation that needs to go into explaining why this happens, but in essence I can see that the differentials du, or the differential du and du cancel out. And what you're left with is dy over dx. Dy dx, which is what we want to find. So in other words, I can find dy dx by multiplying the two derivatives that I just found. So this is equal to dy du is the first part, which is cosine of u, times du dx, which is 2x. And the only thing I don't like about this is I've now written the derivative in terms of two variables, u and x, where it started out the original function in terms of just x. So let's replace u with what it's equal to. So the cosine of, instead of u, remember u was equal to x squared times 2x. So notice that what we did here to find the derivative of this function, again, we started out with the sine of x squared. And we ended up with its derivative was cosine of x squared times 2x. And let's just kind of break this down with what we ended up with here. It looks like this right here is the derivative of our outside function. And if you go back, that's actually what we did, right? We had y was equal to sine of u, our outside function. So dy du was the cosine of the derivative of that. So this is the derivative of the outside function. Okay. And it looks like it's the cosine of x squared. So this is just the original inside function that we started with. This right here is your inside function. That didn't change at all. But then we multiplied that by 2x, which actually, the way we got 2x, to go back here, I said that u was equal to x squared, and the derivative of u, or du dx, was the 2x. So that's the derivative of the inside function. So it looks like what we ended up doing here, again, to just shorten this up, we're always looking for shorter ways or faster ways to find these derivatives if we can. It looks like all I have to do is take the derivative, first take the derivative of the outside function to get cosine, evaluate or substitute into that function the inside function, the x squared, and then multiply that by the derivative of the inside function, the 2x. So that right there, in fact, is chain rule. So we don't call this composite rule. We call it chain rule. There's a reason why. We'll see it's called chain rule. But chain rule is for finding the derivative of composite functions. Now there's two ways to write this down. We're going to write it down both ways. One way is this first form that uses kind of this function notation. The second way uses kind of the notation that we just used to find that derivative of that example. So it says if f of x is equal to g of h of x, f of x is a composite function of functions g and h. It says then f prime of x is equal to g prime, that's the derivative of the outside function, evaluated at h of x, the inside function, times h prime of x, that is times the derivative of the inside function. So it's the derivative of the outside, evaluated at the inside, times the derivative of the inside. Think of that as really kind of three steps that you've got to go through to find that derivative. Derivative of the outside, evaluated at the inside, times the derivative of the inside. There are the three steps you've got to go through. So think of chain rule as a three-step process there. Now, the other way to write this is similar to what we just wrote down, actually. In fact, we wrote it down on the previous slide, that dy dx can be thought of as dy du, where y is the outside function in terms of u, times du dx, where u is the inside function as a function of x. So the product of those would give you the derivative of a composite function. All right, so let's try using this in a couple of examples. And I guess before we go to that example, I should mention why we call it chain rule. We'll see that as you get more and more composite or functions that make up this composite function, you'll end up actually reusing the composite function or the chain rule over and over and over again in finding a derivative. And so what you end up with is a bunch of these derivatives multiplied together. And thus you end up with a chain, if you will, of derivatives that are multiplied together. And that gives you the derivative of that original composite function. Now the number of links, if you will, in your chain, the number of derivatives you're multiplying together, corresponds to the number of derivatives that you started out with. So if I have g of h of x like I have written here, there's two functions, function g and function h. Notice that over here in the derivative, I have to take the derivative of g, and I also have to take the derivative of h. Thus I have two functions that I'm multiplying together there in essence. And if I had three, I'd have three links to my chain, and so forth. Okay. All right, let's try a couple of examples. If you look on page 105, example 1, it says that f of x is equal to x cubed plus 7 squared. Now, one way that you've seen in the past, I guess, to take the derivative of this is just to square this thing out, get a polynomial function, and then take derivative term by term. We're going to try this a little bit better approach in this case. That I see I have a composite function. That as I see I have an inside function, which is x cubed plus 7. And I see that I have an outside function here, which is squared. It's x squared, really, is what I've got there. And so follow your chain rule to take the derivative of this. You first have to recognize it's a composite function, and then use chain rule. So chain rule says take the derivative of the outside function. So in essence, what I'm going to do here is I'm going to kind of ignore the inside function for a moment. And I'm just going to focus on that squared part of it. And think about, how do I take the derivative of something squared? Well, that's a power function. I'd follow power rule. So power rule says you bring the 2 out front. I'm just going to put parentheses there for something that's got to go there. 2 out front times something raised to the first power. There's the first step of chain rule, derivative of the outside function. The second step of chain rule says you substitute in or evaluate at the inside function. The inside function here is x cubed plus 7. And then finally, chain rule says you multiply now by the derivative of the inside function. Derivative of x cubed plus 7 is going to be a 3x squared plus 0. You, of course, could leave off the 0 there, but I'm just writing it all out so you see everything there. And let's just rewrite this here. I've got 2 times the 3, so that will give me a 6x squared out front, I guess I'd write, and then x cubed plus 7. And I would leave it just in that form there. If you wanted to distribute the 6x squared through there, you could, but there is our derivative. All right. So you look at another example. Look at example 2. This one says y is equal to the cosine of x to the 4th power. So y equals cosine to the 4th of x. Now that notation there, by the way, if it helps you to rewrite it, sometimes we rewrite functions. You've already seen that. So it's a form that you can take the derivative of, or at least a form that you recognize or can work with a little bit easier. Cosine to the 4th of x really means you're taking the cosine of x and you're raising that whole thing to the 4th power. The reason I suggest rewriting this is because now it's a little bit easier for me to see this composite function. I can see my inside function is cosine, and I can see my outside function there is the 4th power. So now I'm ready to take the derivative of this. So y prime. Y prime, they said find dy dx. If you want to write it that way, y prime is the same as dy dx. Those mean the same thing, but the derivative of this, it's a composite function, so we're going to follow chain rule. Chain rule says take the derivative of the outside function, so ignore cosine, the inside function stuff so far right now, and focus on the power there. That's a power function, raise to the 4th power. Power rule says you bring the 4 out front, and you take something and raise it to now the 3rd power. I like using those parentheses as kind of a placeholder as we do this. And that's the first step of chain rule. The second step is to substitute in or evaluate that at the inside function. So the cosine goes inside those parentheses. And the third step of chain rule now is to multiply by the derivative of the inside. Now the inside function here is cosine. Derivative of cosine, remember, is a negative sign. And again, we'd rewrite this here just slightly and write it as a negative 4. I'll write it as cosine cubed x sine of x. And there is our derivative. All right, let's take a look at a couple more examples here, actually. Here we've got several functions that make up our composition. It says let f of x equal sine cubed of x squared minus x. Again, if it helps you to rewrite this, I'd suggest that you do it. And I would definitely recommend it here again, that this is actually saying to take the sine of x squared minus x, and you're raising all of that to the 3rd power. That's what the cubing part of this means. So notice that you've actually got 3 functions here that make up your composition. You've got x squared minus x. You're going to then take the sine of that, and then you're going to raise that to the 3rd power. So there's 3 functions that make up our composition. However, for the start of this problem, what we're going to do is we're going to focus on the outside and work our way in. So I'm going to focus on just the outside function, and everything else is going to be the inside function. So in other words, the cubing is going to be the outside function. The sine of x squared minus x, I'm going to think of all that as being the inside function. Even though there's technically 3 functions here, I'm taking just the outside function, and everything else is part of the inside. All right, so let's take the derivative of this thing. Start with the outside function. Like we've said, the outside function is that cubing function. The power function raised to a power of 3. So let's take the derivative of a power function. Power rule says it's 3 times something raised to the 2nd power. That's how you take the derivative of something raised to the 3rd power. And then chain rule says, that's the first step that we've done so far. Second step says substitute in the inside function. Again, the sine of x squared minus x, all of that is the inside function for the moment. So it's 3 times the sine of x squared minus x to the second power. That's the derivative of the outside. Evaluate at the inside. And then chain rule, the third step of it, says to multiply by the derivative of the inside. Now notice the inside function, actually we've already said that, is a composite function. So I have to take the derivative of a composite function. How do we do that? It's known as chain rule. In other words, in the process of evaluating the first derivative here of the outside function, I now have to take and use the chain rule again in order to find the derivative of the inside function. So we can see that it's kind of recursive here in the way that chain rule works if I need to. So multiply now by the derivative of the inside. So derivative of a composite function is this. Take the derivative of the outside function. Sine is the outside function. So the derivative of sine is cosine of something. And I multiply that by, or excuse me, I substitute in first of all, or evaluate at the inside function, which is the x squared minus x. And then I multiply now by the derivative of the inside. And the inside for that function was the x squared minus x. That's just a sum of functions here, so the derivative is going to be, derivative of x squared is 2x, minus the derivative of x is 1. What you'll notice here is that I end up with, in essence, 3 links in my chain. I took the derivative of the cubing function first, and that was right here. And then I multiplied that by, I took the derivative of the next outside function, which was sine, and its derivative was cosine right here. And finally, I took the derivative of my next outside function, which is actually just the x squared minus x, and its derivative was right here. Oops. Let's do that in the same color. 2x minus 1. Okay. Now we'd probably combine this, or we should combine this to make it a little bit nicer here. I guess if you wanted to distribute the 3 through the 2x minus 1, you could. I'm going to write it as 3 times 2x minus 1 times sine squared of x squared minus x times the cosine of x squared minus x. And there is our derivative. All right, let's take a look at one last example here. Again, we've seen some problems here where we have to rewrite them slightly before we take the derivative. We're going to do the same thing here. This time it says that f of x is equal to 1 over x squared plus 1. Now 1 divided by x squared plus 1, that's a quotient. I'd need to know how to find the derivative of a quotient in order to take the derivative of that, at least in that form. And if you reach into the bag of tricks, if you will, the rules that we've learned so far for derivatives, quotient rule is not one of them. We've learned how to take the derivative of a sum, but not of a quotient. So I have to rewrite this. I can't take the derivative of it in its form that it's in right now. But fortunately, I can rewrite this in a form that's a composite function. Instead of 1 divided by x squared plus 1, I could write that as x squared plus 1 to a power, and that would be to the negative 1 power. Okay? So I've now rewritten it as a composite function. I can see now that I've got an inside function of x squared plus 1. I've got an outside function of a negative 1 power. And so we're all set to take a derivative of this thing. Again, once you get it into a form that everything that's written there, you have a rule for finding its derivative, you're good to go. All right, so f prime of x. Follow chain rule. Chain rule says you start with the outside function, the negative 1 power there, and follow your rule for its derivative. A power function, its derivative is negative 1 times something to the negative 2. You subtract 1 from the exponent, don't forget. That's the first step of chain rule. Second step says take the inside function, x squared plus 1, and substitute it back in. That's the second step. And finally, the third step of chain rule says take the derivative of the inside function. So derivative of x squared plus 1, that's 2x plus 0. And let's just rewrite this here. You'd have a negative 2x times x squared plus 1 to the negative 2. You can leave it in that form. If you wanted to rewrite it back in a quotient form, since that's what you started with in this problem, you could write it this way. It would be a negative 2x in the numerator and you'd have x squared plus, x squared plus 1 to the second power in the denominator. Okay, so that is our chain rule.